So what we're going to talk about today are alkynes. Now, in Organic 1, we introduced alkynes, but we didn't spend too much time talking about them. And even now, we're not going to say too much, but we'll at least get one lesson in regarding alkynes. So just a little bit of review here. So first of all, when you're naming alkynes, you use the suffix Y-N-E. Okay, so for example, there's 4 carbons, it would be butane, and the number just indicates where the triple bond begins, because that's what an alkyne is. It's a carbon-carbon triple bond. All right, so the carbons are sp hybridized. And what that means is that the bond angle is 180 degrees, and therefore it gives you a linear arrangement. But also what an important feature is that we have 2 pi bonds in an alkyne. An alkene, a double bond, had a sigma bond and a pi bond. An alkyne is composed of a sigma bond and then 2 pi bonds. Okay, and both of those pi bonds, this is the important thing regarding the chemistry of alkynes, both of those pi bonds can behave as nucleophiles and react with electrophiles. Okay, so how do you prepare an alkyne? What is a way to make an alkyne? Well, if you have a compound that has 1, 2 halogens on it, so 2 halogens connected to adjacent carbons, and you treat that with a strong base like potassium hydroxide or sodium hydroxide, you could get 2 elimination reactions to give you the triple bond. So here's an example of that. So if you have this compound here where I've got a bromine on this carbon and adjacent to that I got a bromine on that carbon, you can carry out 2 elimination reactions. So for example, one elimination reaction can get rid of that HBr, and then another elimination reaction can get rid of that HBr. And then what you have left over then is the triple bond. Okay, so what about reactions of alkynes? What do we do with them? Well, they are very similar to alkenes when you're talking about addition reactions. And that's what we're going to focus on. And we learned about Markovnikov's rule, that functional groups like particularly the OH functional group, alcohol functional group, hydroxyl group, they get added to the most substituted carbon. There's not as much opportunity for substitution with alkynes because of the triple bond, but it still follows that rule. So you can imagine that if you start with a triple bond, do 1 addition, you end up with a double bond. You end up with an alkene. And so because of Markovnikov's rule, and remember the whole motivation behind following Markovnikov's rule is because that's what is the most stable. And so if you stop after breaking 1 of the bonds and end up with a double bond, you end up with the arrangement around the double bond that's most stable, which we have learned is the trans arrangement as opposed to the cis arrangement. Okay, so if you stop after 1 addition reaction, converting the triple bond into a double bond, it forms the trans stereoisomer. And here's a picture of that. So if I had this triple bond and I add 1 unit of HCl, 1 equivalent of HCl to it, now this one we don't have to worry about Markovnikov's rule because it's the same on both sides of the triple bond. It's 3 carbons, 3 carbons. There's no difference in substitution. So you end up with a double bond and the 2 alkyl groups are trans from one another. They're opposite. Now because this is a tri-substituted alkene, you would also designate that as Z. Z-zame Zi. The highest priority groups are on Z-zame Zi. So the chlorine is higher priority than this ethyl. And on this side over here, the ethyl is a higher priority than the hydrogen. Okay, but then you can do it again, reacting with another equivalent of HCl. And this is the interesting thing, is that both of the halogens will go on that same carbon. That's just what happens, okay? And it kind of has to do with Markovnikov's rule, that in a sense that this carbon right here, is more substituted because it's got a chlorine instead of a hydrogen. Okay, but it's not an alkyl group, so you may not be used to thinking of it as in that way. So because this one is the most substituted, when I do the reaction again, the chlorine goes on the most substituted, and that results in the same carbon getting both of those halogens. So that was with a strong acid like HCl or HBr. But remember, we can also add the dihalide, so either Br2 or Cl2, right? And it's the same thing. So it follows the same pattern. Once again, if I have a alkyne and I add, in this case, bromine, Br2, the CH2Cl2, that's just the solvent that this is occurring in. You get the trans arrangement. In this case, the trans arrangement is most evident with the halogens themselves. They're opposite each other. And really, Markov-Nikov's rule doesn't really apply because you're just going to load this thing up with bromines. If it happens again, you break down that double bond into all single bonds. You get the tetra substituted. All right, so let's just do a little practice problem. So we want to predict the products of this reaction. So we have the alkyne, the triple bond, and we're adding two Cl2s. Okay, so I'll pause for a second. You use the example right above to see if you can come up with the correct product. Okay. And hopefully you came up with something like this, where you just put both of those, or all four of those chlorines on these two carbons, converting this unsaturated compound into the saturated alkane. Okay, so we're going to pause for a second. I know, we mentioned at the beginning this lesson is about alkynes, but we got to pause for a second to talk about a different and potentially new functional group, and that is the enol, and you'll see why in just a minute. But we're going to spend a couple slides talking about this functional group, the enol. And the name comes from the fact that it's an alkene where one of the positions has a hydroxyl group attached. So you got the ene from the alkene, and you got the ol like it were an alcohol. So it's an alkene with an alcohol substituent. Now, technically, it's not an alcohol because we remember that we defined an alcohol as a compound where the OH group is attached to an sp3 hybridized carbon. And this carbon is not sp3 hybridized, it's sp2 hybridized. So it's technically not an alcohol, but we also associate that OH when it's attached to a carbon, we kind of just generically say that's an alcohol. But it's not totally wrong to say that it's an alcohol. But the point is, this is unique because of some chemistry that we're going to look at in just a second. All right, what's unique about the enol functional group is that usually it doesn't like to exist in that form. It will rearrange and transform into a ketone. Okay, and the way it does this is it basically just, the oxygen gets rid of its hydrogen and drops it onto the adjacent carbon. All right, and then the double bond shifts to the carbon and oxygen. Okay, so if you're doing arrow analysis here, it gets a little bit weird, but it's like this carbon and the electrons from the double bond kind of grab that hydrogen, but then the electrons that were in this bond between oxygen and hydrogen move down to form the double bond between oxygen and carbon. Okay. Now you already see this weird word here. The name for this is tautomerism, and so each of these is called a tautomer. My mouth today. Tautomer. Okay. Another vocabulary word for you. Okay, and it's like an isomerism kind of situation. But normally with isomerism, you don't break bonds and reform other bonds. So it's only kind of like that in the fact that it's the same formula. There's not a huge rearrangement of atoms, but there's a significant rearrangement of the atoms. So it's isomeric compounds that rapidly interconvert by the movement of a proton. They're called tautomers. Okay, oops. All right, and also I just want to point out before we do advance to the next slide is that the ketone form is more favored. Both forms are present. It's an equilibrium. It's a reversible reaction, but the equilibrium favors the ketone. That's the dominant form. Okay, so why are we talking about this? Because we're talking about addition reactions with alkynes. And so what you're going to see is that I can start with an alkyne, do an addition reaction on it that puts an OH group on the carbon involved in that triple bond, and therefore I create an enol, which will then tautomerize and form the ketone. So that's where we're going with this. We've already learned we've learned a few ways to do this. We're going to focus on two of them. One of them was the oxymercuration. That's what we're really getting to talk about here. So mercury 2 catalyzed hydration of alkynes. So alkynes undergo hydration in acidic solution readily in the presence of mercury 2 sulfate. So we use slightly different mercury compound. Remember that when we talked about it for with alkenes, converting alkenes into alcohols, that was with a mercury 2 acetate This is mercury 2 sulfate. But really, it doesn't matter because it's the mercury ion that's the important thing. It's what serves as the catalyst. Okay, once again, one of the important thing that we learned about this technique, this way, is that it does follow Markovnikov's rule. So that OH group is going to go on the most substituted carbon. Okay? You'll see that what we do when we perform this reaction is that we form the enol, which then rearranges to form the ketone through that process we call tautomerism. Okay, so enol intermediate rearranges into a ketone through the process of keto-enol tautomerism. All right, and so here's an example. So again, we start with the alkyne. It's a triple bond. We're going to add water across the triple bond, and we're going to follow Markovnikov's rule. So in this case, you see that the most substituted carbon is the interior one. Okay, the one at the end is not substituted at all. It just has a hydrogen. So the one that's interior is this more substituted. So that's why the alcohol group goes on that carbon. Okay, so there's your enol. You got the ene right there with the double bond. You got the ol right there is the OH group on the carbon. So we learned about how it can just rearrange and form the ketone. And so, you know, we already added, the color coding kind of got lost in the middle, but one of these hydrogens comes from the water molecule from the first addition, and then the other hydrogen is from the rearrangement, and it comes from the OH group. So that's why they're color coded, you know, magenta over here. Okay, so that's why we had to talk a little bit about enols before we go on to this reaction. Okay, so there's just a little bit more detail about the mechanism. This is not in your handout. I don't expect you to, again, you know, write out this whole mechanism. It might help you understand what's going on and get the right answer if you see in detail what the steps are. So again, the first thing that happens is this mercury ion is attracted to the electrons in the triple bond. You know, the triple bond serves as the nucleophile. This positively charged mercury is the electrophile. So I form a bond there. And again, it follows Markovnikov's rule, which says that the most substituted one is going to be where the functional group goes, the OH group goes. And that's because this is a secondary carbocation, which is more stable than a primary carbocation. The plus charge isn't going to go on this carbon. The plus charge is not going to go on this carbon because that would be a primary carbocation. It forms the more stable secondary carbocation. Okay, so then another water molecule attaches, okay, and forms the oxonium. Another water molecule comes along and takes the hydrogen off of that oxonium to give us the alcohol group, the OH group, the hydroxyl group. So now I've got the enol, I've got the double bond, and I've got the alcohol group. Okay, so it rearranges. So then, once again, we got to displace this mercury. That's what happens in the next step. So acid, a molecule of acid, this is acid catalyzed, this is in acidic conditions. So one of those hydrogens comes from the H3O plus and replaces that mercury. Okay, and then, as I said, this hydrogen is going to move to this carbon, and this double bond is going to move to become part of the carbonyl, to transform into a carbonyl. Okay, so let's see if you got it. Let's practice this. So predict the product of this reaction. And you'll notice that you don't have to worry about asymmetry because both sides of this alkyne are exactly the same. Okay, so there you can check your work. And again, you'll see that the reason why we point out that it's symmetric on each side of that triple bond is because it doesn't matter whether you made the ketone on the left or on the right, you end up with the same product. If it was not symmetrical, you would end up with a mixture of products, and that's what we're going to focus on now. Okay, so as I was saying, that one was simple because it was the alkyne was the same on both sides. But if you have differences, and that's designated here by notice that the R's are different. We have R on the left, and then we call it R prime on the right. So just some different R group. So if they're asymmetric, or if they're different on each side of the triple bond, then you're going to get a mixture of ketones. Okay, so let me color code this a little bit so you can see what I'm talking about. So in this case, notice that we've got an R connected to a carbon, okay? And so the ketone could go on that one. That means that the other side just gets the hydrogens. So that carbon right now doesn't have any hydrogens on it. This is the one that got the hydrogens. So one carbon gets the double bond to the oxygen, and the other one gets the hydrogens. Okay? But the other possibility is that you could have the blue get the ketone, the carbonyl, I should say, and then that R group gets the hydrogens. So you get a mixture if the two are not the same. Now, one other unique thing can happen if the alkyne is on the end of the molecule, a terminal alkyne. So remember that, and we saw this before in the example, but because of Markovnikov's rule, if you have a terminal alkyne, you end up with a methyl ketone. So this will always happen. You end up with a methyl ketone if you have a terminal alkyne. Now that's important because we're going to remind ourselves of another way to put an alcohol to do an addition of an alcohol functional group where it will yield an aldehyde on a terminal alkyne. All right. So all of this, just to remind you, all of this is when we catalyze the process with a mercury 2 sulfate in acidic conditions. So the other way, when we talked about alkenes, that we could slap a hydroxyl group in there, was with hydroboration. Hydroboration was the way in which we could add an alcohol group into an alkene, transforming it into an alkane in the process, of course. But it would put the OH, the hydroxyl group, on the least substituted carbon. So it's anti-Markovnikov. So borane adds to alkynes to give a vinylic borane, and then oxidation with H2O2, hydrogen peroxide, produces an enol that converts to the ketone or aldehyde. It can also produce aldehyde by tautomerization. Okay, don't get lost in all the drawings here. I just, I'm trying to point out a few things. That because this is a BH3, what it means is it can interact with three alkynes and form this intermediate. And then once it does that, then you subject it to the hydrogen peroxide under basic conditions, and it breaks this apart. It breaks all these boron-carbon bonds, okay? And again, because of steric effects, that means that the alcohol group is going to go on the least substituted carbon, the one that's less crowded is really what it comes down to. In this case, it doesn't really matter because it's the same on each side, okay? The same crowding on each side. But if one side is more crowded than the other, then that boron will avoid getting in the way of that bigger constituent. And so it will ultimately put that hydroxyl group in the least substituted or the least crowded position. And so in this case, again, you're going to get three equivalents of hexanone. But the real consequence of it occurs when you have that terminal alkyne. And we just saw in the previous previous method with the mercury 2 sulfate, that it generates a methyl ketone because the carbonyl is formed on that interior carbon. And that's because that's where the OH group was. But with the hydroboration, it puts the OH group on the outside, that last carbon, the least substituted, the least crowded. And so when you transform that into a carbonyl, what it generates is an aldehyde. Okay, so the outcome depends on what method you use to generate the enol. If you use the mercury in acidic conditions, mercury ion in acidic conditions, you get the methyl ketone. But if you use hydroboration, the consequence is one of your products is going to be an aldehyde. Okay, so the product of hydration of terminal alkynes depends on the method used. Okay, so now let's use that information, that knowledge, to come up with the reactants that transform this product into the indicated reaction, this reactant into the indicated product. Okay, so how did we transform this? It's a terminal alkyne. So what conditions were used to do that? Okay, so borane in THF with the second step being the hydrogen peroxide and the OH, the basic conditions. Yeah, so the THF might be a little different. It might not be H2O2. It might be some other oxidizing agent. Okay, so just be aware. The big thing is recognition knowledge. Okay, and when the boron is what gives it away. So we talked about this type of reaction with alkenes, the hydrogenation. That's where you just add H2, a hydrogen molecule, across the double bond. Well, we could do that with alkynes. Okay, and in fact, we can do it twice. You do it once to transform the alkyne into an alkene, and then do it again, transform the alkene into the alkane. Now, like we talked about with the alkenes, this is typically done in a heterogeneous way, where the catalyst is in a different phase as the substrate. The substrate might be a liquid, the catalyst might be a solid surface. Okay, so that's what we see in this as well. But there are a couple different catalysts that we can use. If you want to stop halfway, if you want to generate the alkene, and not only that, but you want to generate the alkene with a cis arrangement, so the cis stereoisomer, then you use what's called Lindlar's catalyst. I don't expect you to know what it is, but I do have an example of it. Again, it's variable. Different research groups use different recipe. But for example, you've got palladium that's what's called poisoned with or contaminated with. The key thing is the lead. The lead is what enables you to stop it halfway to where you get the cis arrangement in the alkene. So you start with the alkyne, you add a hydrogen molecule. You can see where those two hydrogens get added. It's a syn addition. They get added to the same side. And that results in an alkene where the R groups are also cis. They're on the same side. And then if you wanted to, stop there and utilize this for some other reaction, you could. But if you just wanted to go all the way to the alkane, you just would use an unpoisoned catalyst, which would just be palladium mounted on carbon or plated out on carbon particles as your catalyst, and you could, reduce it all the way down to an octane. Okay, but the connection here, you need to make Lindlar's catalyst cis. Lindlar's catalyst cis, that's what you need to remember. So addition of H2 using a deactivated palladium on carbon as a catalyst, the Lindlar catalyst, it produces the cis alkene. Okay, well, what if you didn't want the cis alkene? What if you wanted the trans alkene? Well, that's where you do something kind of interesting. You reduce it with sodium or lithium metal as a reducing agent, and you do it in liquid ammonia as the solvent. That does not sound fun to work with, liquid ammonia. Okay, and one of the interesting things about this, this is chemistry that you use in quite a lot of different applications. But anytime you do this, the sodium or lithium, when it's dissolved in liquid ammonia, you see it right here, it's this really intense blue color. That's the color of a solvated free electron. Okay, so if electron is in solution, it's this intensely blue color, which is kind of cool. All right, and what you need to know about it for today's purposes is not that it forms a nice blue solution, that it forms the trans alkene. Okay. So if you start with the alkyne and you add an H2 across it, well, you add hydrogen to it. It actually comes from the ammonia. We'll look at the mechanism in just a second, but the hydrogens come from the ammonia molecules. It adds in a trans way. Okay, so the point is that if you're in a research group and you're trying to build a molecule, remember that organic chemists, I think a great term for those guys are there are molecular architects. So they're trying to build a certain product, and they need it to be a trans alkene. Then they can maybe in a previous step, make the alkyne and then reduce it with lithium or sodium in liquid ammonia to get the trans alkene. Okay, so again, here's the mechanism. So you start with the alkyne, and you just expose it to lithium. Lithium really wants to give up an electron, so it does. It gives up an electron to this. You can see it adds to this carbon on the left. That's one electron that came from the lithium. Well, in order for that to happen, this triple bond has to break, and it dumps the 2 electrons onto the other carbon. So that gives the other carbon a low pair and a negative charge. Well, that's going to pull a hydrogen off an ammonia molecule. Okay, and so that's where we get one hydrogen from. And then it happens again, but it's going to happen in kind of an anti-form where it takes on another electron to give you the carbanion again. And so that's going to react with ammonia molecule to take a hydrogen. Okay, so that's how you get the 2 hydrogens on opposite sides, and then you end up with the trans alkene. What would be the product if we have this alkyne, 2-octyne, and we expose it to lithium in liquid ammonia? So I'll give you time to do that. And I'll go ahead and let you just work on this one below here, where you have the product, but you want to draw the structure of the alkyne that would be the starting material, the necessary starting material. And also notice that the reaction arrow is bereft of reaction conditions. I didn't tell you what the reaction conditions are. So provide those as well. Okay, I'll show it to you a little bit more pretty here in just a second, but just to kind of check your work, that again, you got in your notes today, but make sure you remember when you don't have your notes that if you reduce this alkyne with lithium and liquid ammonia, what you get is the trans stereoisomer, okay? So you end up with a double bond, so the triple bond goes down to a double bond, and the rest of the carbons are opposite each other, the hydrogens are opposite each other. For this lower one, you got to make sure you have the right number of carbons. So there's 2 carbons on the right side of the benzene ring here. So there's 1 carbon, there's the other carbon. Okay, that's part of your alkyne. So it's a terminal alkyne. And then what the conditions are, and again, it's going to be prettier here in just a second, so I won't write it down. But this is where when you have the methyl ketone as your product, and you have a terminal alkyne, that means what you reacted with was the mercury 2 sulfate in acidic conditions. Okay, so the triple bond transforms into this methyl ketone through tautomerization. H2, yeah. The big thing is the mercury and acidic conditions.